Hello everybody, thank you for joining today. My name is Manam and today we're going to be talking about wave period and frequency. Now, some of our learning objectives include to understand what is meant by period and frequency in a wave's context and to recall and use the equation that frequency in hertz is equal to 1 over the time period in seconds. Now, you should already know the different types of waves and the features of those waves. Now, we want to understand the difference between frequency and time period. We record waves transfer information and energy without transferring matter. So waves move throughout space all around us. Frequency describes, let's highlight that here and let's do it in red. Frequency describes the number of waves passing a fixed point in 1 second. That's what frequency is. Frequency is just looking at how many waves pass through a single point. So let's take point E here. If, say, 10 waves pass through point E in 1 second, you would get a frequency of 10 hertz. Hertz is the unit of frequency. Now let's move on to period. Period, let's do that in a different color, is the time taken for one complete cycle of a wave. So if we had a wave here, it went up, it went down, and it went back up again. However long that whole process took, that is the wave's period. Now we want to look at how these two are related. So the equation for how these two are related here is frequency in hertz is equal to 1 over the time period. Now time period is big T here. Don't get confused with temperature. It is time period, so this is in seconds. Now, so if we simplify this a bit, we can get the relationship between frequency, that looks like an L, frequency equals frequency 1 over the time period. So if we have a very high frequency, so we have a lot of waves passing through a point in 1 second, that must mean that the time taken for each wave must be very, very, very small. And that makes sense, right? If you want a great many things to fit in a very short amount of time, each one of those things should take a very small time in of itself. Okay, now we're going to try a worked example. But first I'm going to introduce a new concept called wave speed to you. Now, wave speed is described by this equation over here. V equals f lambda. Now straight away we know that V is velocity, which is measured in meters per second. F, we learned, is frequency, which is measured in hertz, and lambda is our wavelength, which is measured in meters. Arrow on it as well. Now this equation here links together frequency and wavelength, lambda, to give you the velocity of the wave. Now this is going to be very important in some questions that we're going to do, so hold on to it. Now let's start our first question. Some students are investigating waves. They produce waves by moving a piece of wood up and down in a tank of water. This diagram shows the waves over a distance of 60 centimeters. Now, our first question is, state the number of wavelengths shown in the diagram. As always, we're going to highlight our keywords first. I state the number of wavelengths shown on the diagram. It's not saying calculate the length of the wavelength, it's saying state the number of wavelengths. So let's have a look at our diagram. We remember that a wavelength is the distance between 2 points on a wave that are identical. So here we have 1 point on a wave. Now where's the next identical point? Well, it's over here. Where's the next one? It's over here. Then over here, and finally over here. Now some students might get confused and think, oh wait, that's not a complete wave. It is, because these 2 points here and here are still identical, even though there's no top point. So now we join up our dots here to find out the number of wavelengths. So that's one wavelength there, then we have another one here, and we have another one here, then we have another one here and here. So 1, 2, 3, 4, and 5. So state the number of wavelengths shown. Well, 5 wavelengths are shown in the diagram. So that's our first mark done. Now the next question, calculate the wavelength of those waves. Okay, so the number that we're given here for the entirety of the waves is 60 centimeters. And we know that we have 5 waves. So all we do is divide 60 by 5, and that gives us 12 centimeters for the waves. But wavelength is given in meters, so we do 12 for 100, and we get 0.12 meters. And that's our answer for wavelength. And that's it done. Now let's have a look at our second worked example. The student produces a different wave. This wave has a frequency of 1.7 Hz and has a wavelength of 8.0 centimeters. As always, we're going to highlight our keywords. Calculate the speed of this wave. So remember in the last worked example, I told you to hold on to that wave speed equation? Well, we need it now. V is equal to F lambda. F multiplied by lambda. What these letters actually mean. V is equal to the velocity of the wave, which is in meters per second. F is equal to the frequency of the wave, which is in hertz. And lambda is equal to the wavelength of the wave, which is in meters. But do we actually need to convert our wavelength here into meters? If we look at our answer line here, the answer line is asking for it in centimeters per second. So we don't actually need to convert our values here, but we can still use this equation. So let's do 1.7, which is our frequency in hertz, multiplied by 8.0, which is equal to our wavelength, and that equals 13.6 centimeters per second. Okay, now all of our values here in the question are given to 2 significant figures, so we should also give our final answer to 2 significant figures as well. 13.6 to 2 significant figures is 14 centimeters per second, and that is our answer there.